Hi everyone, welcome back. In this video, I will review over molecular geometries and polarity from material you learned from first semester Journal of Chemistry. So let's go ahead and get started. All right, the simplest type of geometry is with two electron groups. Now, electron groups, if you look at the bottom of this figure here, are focused around the central atom. So you always look at the central atom and count the number of things attached to it. And what I mean by things, I mean like if there's a lone pair, a single bond, a double bond, a triple bond, or even a single electron. And as electron groups imply, they have an overall negative charge. And these geometries are all based on the Vesper theory. So Vesper stands for valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory. And as that last letter of this acronym stands for is repulsion, right? They don't like each other. And so they're going to spread out as far away from each other as possible. So if we have something that is two electron groups, the maximum bond angle they could form is 180. And so these types of molecules are linear in their electron geometry and linear also in their molecular geometry because they're zero lone pairs. And this is an example of carbon dioxide. And I like to draw just generic ball and stick models where I make the central atom a dark circle and I make the outside groups, whatever they may be, outside electron groups, these little open circles. All right, so if you have three electron groups, and let's just start with the three bonded groups with zero lone pairs, the maximum bond angle three groups around a central atom can form is 120. And we call that trigonal planar because if you actually look at the molecule, it looks like a triangle. And if we were to rotate this 90 degrees backwards, it would be flat, right? It would be a plane. And the little ball and stick model looks just like what you see here, representing the true 120 degree bond angle, as opposed to a lot of times when we draw loose structures at first, the bond angles are not correct. But then when we look for the 3D representation, we want to make sure we indicate those bond angles as such. All right, so with the three electron groups, you could have molecules that have two bonded groups but one lone pair. Their electron geometry is reflected from the electron groups, and so it still kind of has a trigonal planar geometry, and that's why the bond angle is close to 120. But if we look at the molecule itself, it's not trigonal planar anymore, it's more of a bent shape. So that's where that bend comes from. And so what I like to do with these little ball and stick models is I like to replace one of the groups with the lone pair. So the lone pair needs a spot. It's obviously participating in repelling these two groups down. Like these are not linear anymore, right? This is not what's happening here. This lone pair is repelling and pushing those bonded groups away from itself. And it does so actually even more than another bonded group would do. That's why the bond angle here is actually less than 120. All right, so for electron groups, if we have four bonded groups but zero lone pairs, the maximum bond angle that four groups around a central atom can go is 109.5. So once again, with this Lewis structure, it shows it as 90, but that's incorrect. and actually can form a wider bond angle. And this is tetrahedral geometry for both the electron and molecular. And the way we draw this in 3D, our 3D representation, is two of the bonded groups are in the plane, and that 109-degree bond angle is represented here. One group is coming at you, and we use a wedge. And then one group, that's this group here, it's coming at you, so we always use a wedge. And then one group is going away from us, and that's where we use a dashed line. So this is how we represent the 3D geometry on paper, right? This is how we represent this on paper, is using wedged and dashed lines. And once you learn kind of like these like ball and stick models that you can draw on paper for the electron geometry, we can use it for that entire series. So I can use this model here to draw trigonal pyramidal correctly in 3D, and I can also use this model for the bent as well. And this will be really helpful for you when we get to the more complicated molecular geometries. All right, so when we look at something that with one lone pair still has 4 electron groups, so that's why it's still tetrahedral electron geometry, but trigonal pyramidal, because one of those bonded groups is replaced with a lone pair. All right, so once again, I'm going to use my previous model and just kind of mimic it. I'm going to make 3 of the groups the bonded groups, and when I replace one of the bonded groups, I replace the top one with a lone pair. And if you were to build this model, and you can kind of see it maybe a little bit better here, it's a triangle base, but there's like a point to it. It looks like a pyramid, and so that's why this one's called trigonal pyramidal. And then finally, we have, for the 4 series, we have 2 bonded groups, 2 lone pairs. So still tetrahedral electron geometry, but this one now, because it has 2 lone pairs, is bent. Not linear in the way it kind of looks here. And so the way we represent bent, in many cases, we just show it with a slightly smaller bond angle than the previous one we saw before in the 3 electron group series. Like that. So typically we don't always show the bold and dashed lines. You could use this trick and for example, put, if it's H2O, you could put oxygen here and hydrogens here and then lone pairs here and here if you're illustrating that. But most of the time we keep it such that the bonded groups are in the plane, understanding that it's still tetrahedral geometry with the lone pairs. One's bold and one is dashed. All right, now let's say our molecule has 5 electron groups. So 5 bonded groups, 0 lone pairs to start. That is a trigonal bi-pyramidal geometry. And these molecules have 2 bond angles. So this is what it looks like here. Let me draw it on the paper. So 3 of the bonded groups are in the plane. 1 is coming at us, and 1 is going into the paper. So these are the 3 that are in the plane. One's coming at you and one's going into the paper there. All right, so I like to think of these molecules, if you thought of it as like the world, right? And these 2 points would be your axis, and then this is the equator, and so that's equatorial. And so I like to label axial AX, and then equatorial, EQ, EQ, and EQ. All right, you'll notice that the bond angle between an axial and equatorial position is 90 degrees, and the bond angle between equatorial positions is 120 degrees. And this one's trigonal bi-pyramidal. As you can see, in the equatorial position, it looks like a triangle, but on each axis is a point. And so that's why it looks like it's two pyramids stuck together. And so that's why it's trigonal bi-pyramidal. Now, what happens if we have 4 bonded groups and 1 lone pair? Now, with this series, it's important to remember that lone pairs take up a lot of space. We discussed that when we were talking about why the bond angle for the bent shape is less than 120 and not exactly 120 like it is in trigonal planar. It's because it's taking up a lot of space, and that's why I like to show it as a balloon. It's like a big balloon taking up a lot of space. And so with this particular series, lone pairs will only take up the equatorial positions. Lone pairs do not want to be in the axial positions because then they're too close for comfort to too many groups, and that's a 90-degree bond angle as opposed to like a 120. So let's go ahead and draw that. It's important that you remember that, otherwise you won't get the correct geometry. So for this one here, and like I said, you can replace any of the open circles with a lone pair as long as it's in the equatorial position. So I'm going to put it here and keep everything else the same. I'm mimicking the model that I've drawn. You only need to learn the electron geometry models, the main ones here, like I'm showing, the trigonal planar, tetrahedral, trigonal bi-pyramidal, and then we'll learn octahedral in a second. You just need to learn this one here for this series and remember that lone pairs just take up equatorial. And then that way you'll always get the correct bond angles when you draw the 3D representation of it. And so this one's actually called a seesaw, and if you were to flip it over, it actually, and build the model itself, it does act like a seesaw. All right, so if we have 3 bonded groups but 2 lone pairs, then we still have a trigonal bi-pyramidal electron geometry, but now we have something that looks like a T, and that's why it's going to be called T-shaped. And for this one, I'm going to strategically put the bonded groups where it will be most apparent that it's a T, and I will put the lone pairs here. Once again, you could have put the lone pair here or here, and it would still have been T-shaped, or I would say you could have put it over here instead as well. It would have been T-shaped, but it just maybe not as apparent on a piece of paper or drawing. You would have to do some rotating in your mind of the shape to visualize the T. So I like to draw it like this just so that the T is very apparent to me. All right, and the bond angles are less than 90 degrees because these lone pairs are kind of pushing these groups a little bit farther down. They're repelling them even more. All right, finally for this series, we have 2 bonded groups but 3 lone pairs. So still a trigonal bi-pyramidal electron geometry, but these molecules are linear. Similar to kind of the linear that we saw up at top, right? The bond angle is 180. It looks a little bit different though in its little ball and stick model because the central atom has 3 lone pairs around it. So something that looks like this. All right, the Electron Group Series 6. Let's start with 6 bonded groups but 0 lone pairs. This is octahedral. The maximum bond angle is 90 degrees. And it will look something like this. So let's draw it. So the central atom, 2 of the groups are in the plane. So these are the 2 groups in the plane. 2 groups are coming at you and 2 are going into the paper. So remember, the ones going into the paper, we use a dash. And the groups coming at us, we use a wedge. And that's how you would do a 3D representation of the octahedral group. And each of these bond angles is 90 degrees. Did not mean to erase that. Let me draw that again real quick. What I was going to say is that each of these groups is 90 degrees from one another. So when we start putting in the lone pairs, it doesn't really matter where you put the lone pairs in this series here. Because they're all the same bond angle. It's different with the Trigonal Bi-Pyramidal. We said that you can only put in the equatorial position, but for octahedral, it doesn't matter. All right, now let's say we have 5 bonded groups but 1 lone pair. The shape we're going to see for the molecular geometry is square pyramidal. So I'm going to replace one of those open circles with the lone pair. I replaced the bottom one so that you could see the base is a square shape, and then there's a point up top that makes it like a pyramid, and so that's why this shape is called square pyramidal. And then finally, we have 4 bonded groups, 2 lone pairs. Lone pairs do want to be as far away from one another as possible. So I'm going to put them on opposite ends here and then keep the bonded groups left over from the shape that we've drawn before. And what you will notice is that it has a square base, and if we were to rotate this 90 degrees, it would be flat. It'd be like a plane, and so that's why this one's called square planar. All right, so I wanted to briefly discuss polar and non-polar, and I'll dive into that topic a little bit more again in the next video as well. This is something you should have learned in your first semester journal chemistry, and it's going to be very useful for second semester general chemistry when we learn about intermolecular forces. And so that's why I'm reviewing over this material now, so that you feel prepared for what is to come. So, polar is something that has a dipole moment, an uneven charge distribution. And I'm going to represent polar as, capital P here. Nonpolar is something that has a very even charge distribution. And then some of these molecules, we might not be able to determine if it will be polar or nonpolar in the ball and stick model form because we don't have actual atoms attached to them. And so I'm going to just say, hey, if you have this particular molecular geometry, it really just depends. It depends on what are the bonded groups attached to it, and if they're all the same bonded groups or if they're different. And so that's one that won't have a definitive answer, and you'll see why, right? Okay, so for example, the first molecular geometry linear. If something is symmetrical and you have the same atoms on the outside, like for example, carbon dioxide is a great example. Carbon-oxygen bonds are polar covalent, right? That oxygen's very electronegative. However, these little dipole moments are going in equal and opposite directions. And so, because carbon dioxide is linear and has that symmetry, it's overall nonpolar. However, with linear molecules, there are linear molecules where both atoms on the outside are not the same. So for example, if you had an oxygen on this side but a sulfur on this side, those dipole moments are different from one another, and therefore they would not cancel one another out. And so for this symmetrical molecule, or molecular geometry shape, it really depends what the actual molecule is. Same goes for trigonal planar. Now this is also a very symmetrical shape. So if you have the same atoms on the outside, then you would end up with a nonpolar molecule. Just like with this boron trifluoride molecule there. It's, nonpolar there. However, because you could have 3 different bonded groups attached to the central atom, this geometry really depends, molecule to molecule. Now with the bent shape, we have a lone pair here. And you notice that these 2 bonded groups are not linear anymore. And this is not a symmetrical shape. So if you have bent, then we are working with something that is polar. For tetrahedral, very symmetrical. So if you have the same groups attached to it, like if these were all chlorines attached to a carbon, those dipole moments would cancel out and would become nonpolar. However, it just really depends. You could have, 2 bromines attached and 2 hydrogens. And if that happens and you break up that symmetry, you would end up with a polar molecule. Now, as you see here, when we add a lone pair, we do not have any symmetry anymore. And so these types of molecules, if they have polar covalent bonds, then they are definitely polar overall. And same for the bent shape. And so what you're noticing is that the electron geometries with no lone pairs, they're very symmetrical. Same thing with this one here and octahedral as well. So if you end up with the same groups, and in this particular table here, that's what they did, then all those little dipole moments would cancel out and you end up something that's nonpolar. But it really does depend, because you could attach other groups besides all fluorines or all chlorines, which would make the molecule more polar. And as we see with the seesaw, there's no real symmetry here. Like, these dipole moments couldn't cancel one another out. They're not in equal and opposite directions. And so this type of molecule is generally polar. Same thing with T-shaped. However, with the linear, it really depends. Once again, if we had 2 different bonded groups attached, they each have different dipole moments. We already discussed that octahedral with that symmetry. It really depends on what's attached on the outside of the central atom. But with the square pyramidal, there's no real symmetry here, so these are generally polar. Now we come back to square planar, and there's some symmetry here. We could see that these could cancel out and these could cancel out, and this is the same. So therefore, overall, these can be, and like this one here, nonpolar. However, it just depends. Maybe we don't have the same type of atoms attached to the central atom. And so make sure you review over polar and nonpolar from your first semester Journal of Chemistry. Make sure you're practicing with molecular geometries so that you can predict if a molecule will be polar or non-polar overall. It will help in the discussion of intermolecular forces in the future. All right. Thank you for watching, and see you next time.